Okay, so I hope you can all hear me. So I'm Thomas Johansson, program co-chair, together with Jung-Hee Chon, and I would like to welcome you to PQCrypto 2022. I will just give a very brief introduction to some statistics and so forth. So this year we had 66 submissions. A few of them were withdrawn just before the reviewing process started. And in the end, we accepted 23 papers, which brings the acceptance rate to about 35%. The process was kind of standard process. Each paper reviewed by at least 3 PC members, and it was a standard process, meaning that there were individual reviews at first, and then there was a longer discussion phase among the PC. Each accepted paper has appeared in lecture notes in computer science. You have access to it with papers of 20 pages and then an additional up to 10 pages for references and appendices. So in the program, we also have 3 invited speakers, Peter Schwabe, Andreas Hülsing, and Ward Bullens, and you will see their appearance later. And we also voted for a best paper award among the PC, and it was given to the paper breaking category 5 things plus with SHA-256 by Perlner, Cooper, and Kelsey. So the hard work was done by the program committee. So I would like to thank all of them for their efforts in producing the program. They are many, so hardly readable, but here is the program committee. And finally, I would like to also thank a lot our general chair, Tanja Lange, for making all the arrangements for this event, and I hope everything will just run smooth coming along. So thanks to you all, and welcome to the program to come. So I will hand over to the first session.
So, hi everyone, welcome to this first session on implementation and side channel attacks. The first speaker is Marcus Krauss. So on efficiently masking polynomial inversion at arbitrary order. And so Marcus, you have 10 minutes, and then we will have a session of questions, and everyone, you can ask your questions on the Zulip chat, and I will ask them to Marcus after. So, Marcus, it's up to you.
Thank you. So, hello everyone. I'm presenting a joint work here with Jan, Tim, and Georg. Georg was actually supposed to give this talk, but he's not feeling well today, so I jumped in. The motivation for our work is that in multiple post-quantum crypto schemes, we need to invert polynomials. And here you see examples, the key generation of bulk N2 and streamlined N2 prime. And the only thing that is really important here is highlighted in red. So in each scheme, we have polynomials that need to be inverted. And the polynomials are also part of the private key, so they need to be kept secret. And we have to protect them also against side-channel adversaries. That means for we need constant time implementations to prevent against timing attacks. But for more powerful local attackers that can measure the power consumption, we want a masked implementation as a countermeasure. So in our work, we present the first procedure and implementation for masking polynomial inversion. and it's very efficient. If you're familiar with the average cost of masking, our results might surprise you. And the algorithms, they work for arbitrary masking order with a disclaimer actually that I will come to later. So yeah, the basic idea. A short introduction to masking. How does masking work? It's based on Shamir's secret sharing. The setting is that we have an attacker that can retrieve secret values by measuring the power consumption. And as a countermeasure, we split the secret values into random shares, and the attacker now needs to retrieve both shares to get the value. This makes the attack much harder. And in this example, our secret A is split into two shares, A1, A2, and computing A1 XOR A2 gives us A. In this example, we have two shares, so this is called first order masking, but it is expandable to an arbitrary number of shares, and we call it higher order masking. In this example, we have a Boolean sharing because the shares are combined with XOR operations. So now we can safely store values, but what do we do when we want to operate on values? And this is actually easy for operations that are linear in the masking domain. So for example, if I want to compute A XOR B, I can do the operation sharewise. So I can compute A1 XOR B1 and A2 XOR B2, and it's the correct result already shared. So as you can see, the expected overhead is usually around 100% for first order masking because I have to do the operations twice. So there are other masking domains, for example, the arithmetic or additive masking. So instead of an XOR to combine the shares, we now use an addition. And we choose our masking domain depending on the operations that we want to do on our secret values. Yeah. So we see in this additive masking domain, it's very cheap to do an addition. So the observation here is for functions that are linear in the masking domain, it's very cheap to perform them. So the question arises in which masking domain is the polynomial inversion linear. So this would be the polynomial multiplicative masking domain. So each share is now a polynomial, and we combine them with polynomial multiplication. Multiplicative sharing is normally not used because it has a problem. Because if the attacker sees one share with a zero value, this immediately reveals that the secret value is zero. But in our setting, this is not a problem because zero polynomials are not invertible, so the zero value does not appear. So we saw that we can have different masking domains for different operations. And when we want two different domains in the same algorithms, we need to convert between the domains. So in our use case, we're starting in an additive with an additive sharing, and we want to get to a multiplicative sharing. So what we do now is we sample a random polynomial R, and then we multiply both additive shares with this R. And then we invert this polynomial R, and this is already the multiplicative share M2. And now we basically have three shares, but we want to go back to two shares because we do first order masking. And what we do now is we combine the additive shares with an addition, and this becomes the multiplicative share M1. And we can do so, we can combine the additive shares, and we won't leak A because it's protected by this randomized R. So now we are in the multiplicative domain, our conversion is finished, and now we want to do the inversion, and we could do so by inverting both shares individually, to get the inverted A. But there's one thing that we can observe here. If we do this conversion and then directly do the inversion, we basically invert the second share two times. So these inversions can cancel each other out. And so what we can do is we can omit them. And this idea scales very well for higher order masking. So when we have more shares, we always have to do one inversion for this A to M, so additive to multiplicative conversion with the inversion immediately afterwards. And for further operations, we usually would do now a conversion back to the additive domain. And we have algorithms for this in the paper. We implemented our algorithm on the Cortex M4 and did the t-test evaluations there, and for the first order masking, and for 100,000 traces it showed no leakage. And more interesting probably is our performance evaluation. So we measured the speed and cycle counts on the Cortex M4, and in our first use case N2, have a look at the unprotected operations. You can see they are already very expensive on the Cortex M4. So, but what is more important, the inversion is much more expensive than the multiplication and addition. So this performance gap is what basically makes our masking approach so efficient, because our masking the inversion only needs extra multiplications and additions, but no extra inversion. So as a result, our first order A to M conversion with inversion only has a 35% overhead versus the unprotected inversion. And in the second use case, Bike, look again at the unprotected operations first. There's a huge gap between multiplication and inversion. Yeah, it's even more extreme than in the N2 case, because the polynomials are here longer. And as a result, the overhead of our masking is even smaller. It's only 11%. And as a reminder, usually you expect an overhead of around 100%. So this is a great performance result here. As a conclusion, we have found a very efficient method for masking polynomial inversion. In the paper, you also find our M to A conversion, so the back conversion, and all conversions work for any masking order. But as I said, we have a disclaimer here. A very recent work by Coron et al. shows the theoretical vulnerability of our A to N conversion for the third order and higher. But we are confident that we can fix this with more randomness, and for practical implementations, usually only the first order masking is relevant, which is not affected here. So for future work, it would be nice to have some formal proofs of our algorithm so that we can prevent disclaimers like this one. This is the end of my talk. Thank you for your attention.
Thank you for your presentation. It was very clear. So you can ask your question on the Zulip chat, and maybe I can ask a first question. So how hard do you think formal proof will be how hard is it to write formal proof?
Yeah, that's a good point. I have actually no experience with this. So basically what we want to show is, let's start with the attack that was found for third orders and higher. Basically, for the conversion, you always want to show that you always need, let's say we are in the first order masking, you always need 2 shares to retrieve the secret value. And if there is at one time a combination of less shares, then basically your conversion is not secure. So for a limited masking orders, you can do this exhaustively, checking. This would be one option, but and I guess it makes sense because, I don't know, at some point, let's say, I don't know, 7th order masking, it doesn't make sense anymore because it's too expensive. This would be one idea.
And so you implemented your conversion, and is your implementation just for? Do you have to do the implementation for each crypto system, or is it generic? Can you use it for any inversion in any crypto system?
Yeah, so our algorithms are generic. So basically what we did is we went and took the fastest implementations of the crypto systems available, And what we are using are like the multiplication routines, and then we have to do the implementation individually according to our algorithms.
Okay. Are there other questions on Zulip? I don't see any, but okay, maybe we can continue with the next talk. And if you have questions, we can come back to them at the end of the session.
Okay, thank you.
Thank you very much for your presentation. So the next speaker is Thomas Chamberger.
Hello, everyone.
Hi. Hello. I let you take your. You want to share your screen?
I'll try this, and if this doesn't work, I also uploaded the slides.
Yes.
Let's try. Okay, you can see my screen. You can hear me. Then I guess we're ready. Okay. Hello, everyone. My name is Thomas Schamberger, as was kindly introduced. I'm a PhD student from Technical University, and I'm going to present you a power side channel attack on the recent version of the PQCrypto system. This is joint work together with Lukas Holzbauer, Julian Renner, Antonia Wachter-C, and Georg Siegel. So let me introduce you to our attack target, the hemi-quasi-cyclic HQC algorithm. It's a code-based CAN, and it's currently a fourth-round alternative candidate in the NIST competition. Here you can see the PKE version of the crypto system, and HQC is based on a code concatenation of two error-correcting codes, which are here abstracted as encode and decode. And the algorithm works in a way that we first encode our message that we want to encrypt, add some error onto it. We compute the second part of the ciphertext. We feed it into the decryption algorithm, and with the knowledge of our secret key polynomial y, we can then, after multiplication with u, subtract the amount of errors in this v such that decoding works again. If you don't know why, then the amount of errors in this stuff that is fed into the decoder is too large, and then decoding fails. The HQC CAN uses a variant of the Fujisaki-Okamoto transformation to achieve a chosen ciphertext secure CAN. How does such a chosen ciphertext attack work? So we feed in some ciphertext into the decryption, and we as an attacker want to observe some property of our secret key y by looking at the output of this decryption. And for this chosen ciphertext attack, we have to put in invalid ciphertext here for the decryption. The idea of this FO transformation is then to re-encrypt our message, and then we check if our resulting ciphertext is the same as the input. If this is the same, then we have a correct ciphertext and we can release the output. If this is false, then we don't release anything and the attacker does not gain any information. For the HQC algorithm, this looks like the following. So here we have the decryption part of the algorithm, and here we have the whole re-encryption part. I have to say that for this re-encryption to be deterministic, we need to sample the same polynomials here, and this is done by obtaining a seed for the sampler directly from our message to this hash function G. Here in the side channel context, and therefore we can gain information about any of these building blocks, and with that we don't have to get the result released, but we can just use this information and then mount the chosen ciphertext attack. And this is what this paper is about. So what we do here is we perform a power side channel attack directly on the decoder here, and there's also some other works presented at CHESS 2022, the first one by Uno et al., which target this computation of the hash function here, and by Guo et al., which exploit the timing side channel and the rejection sampling step during the sampling of these random polynomials. Let me sketch you our general attack idea. So we're interested in our secret key polynomial y. This y is of size of the concatenated error correcting codes, and it is very sparse. So if we observe that if we set u to the one polynomial and v to a valid code word of this code concatenation, we can view y as an error onto this code word. And then we feed it in a decoder, and if we gain any side channel information about the decoding, we can infer on the error. So our goal is to find the support of v, which is very sparse, and we can view this v as building as different blocks of the inner code of the code concatenation. And this here in the recent version is one input to the read-malloc decoder. And we assume that we have a side channel oracle that gives us information about this decoding result here. And if we have that, the attack steps are the following. First, we set u to 1, and we find a v such that we are directly at the decoder boundary. This means if we add an additional error, we will increase the error over the boundary, decoding fails or decodes another code word, and we can observe this to the side channel oracle. With that being said, we can then test each individual bit, so we can flip the bits and then check if we see anything in the side channel oracle, and then from that infer on y. Can be seen that this is directly dependent on the type of decoder and also on the error correcting code. Has to be said that for the third round version of HKC, the authors changed their error correcting codes from a repetition code in combination with a shortened BCH code to a read-malloc code and a shortened read-Solomon code. And with that, such read-Solomon codes that are used in the third round version are decoded using a different decoding approach, namely maximum likelihood decoding. And with that type of decoder, the decoding result depends on the number of errors, but also on the support of the error, so the position of the error in the code word. And this leads to the fact that the power side channel attack of Une et al. Is not working in practice, since it is based on a bounded distance decoder. It is only dependent on the number of errors. And we show a counterexample and simulation results using ideal decoder results in our paper. We then find an attack strategy that works even in the presence of such a maximum likelihood decoder, and we base our attack on what we call a close to zero oracle. For that, we have to find a side channel oracle, which gives us information about the decoding result of the read-malloc decoder, and we are interested if this is decoded to the zero code word or to something else. And given that, we can, for the first step, we can find a read-malloc code word that the second step, where we invert the individual bits, our oracle result is always valid depending on E. And we make sure that there are also no ties possible in the decoder. And with that, we allow to follow the general attack strategy again, even in the presence of such an event decoder. We show a proof in the paper for this restriction, and this restriction is valid with very high probability for all the HKC parameter sets. We also verified our attack then with simulation of perfect oracle calls from the decoder. We can compare our attack to the timing side channel attack by Hu et al., which is non-deterministic. And in this table, you can see the required amount of oracle calls. So as said, we have to do our attack for all the different inner code word blocks. So we have to have an additional factor here. And this are our required oracle calls. And for the timing attack by Hu et al., it is non-deterministic, so they show the median of around 6,000 attacks. And we can see it has an overhead of a factor of about 16.34. And to be fair, we also found that the attack strategy of Hu et al. Can also be used with our close to zero oracle. We also simulated this and we showed a median of required oracle calls, and we also can see that this is quite some overhead on the required oracle calls. Now, let me discuss quickly about which side channel targets we can use to build our close to zero oracle. Our work focuses mainly on the decoder here, so we show how to use a power side channel of the read-Solomon decoder during the decoding step to gain our oracle results. We also discuss how we can use the oracle on the hash function here on the Shake 256 for our attack. The thing is that for this, we have to kind of change our attack strategy a bit, since this here is dependent, can only distinguish between different messages here. So therefore, we have to change our attack strategy such that one read-malloc decoding result influences our message here. We can observe this through this hash function. But sadly, the timing attack on the sampler does not work since it requires a certain structure of the message such that unexploitable or observable timing difference results. So as a conclusion, we showed that the updated version of HQC requires new attack strategies. The used with Muller decoder uses a maximum likelihood decoding, which breaks the attack assumption from Uni et al. We show a new attack that we also give a proof with our close to zero oracle, and we can build this oracle through directly attacking the Reed-Solomon decoder, or we can also use the oracle shown on the shake hash function. Timing side channel is not usable for attack. In the paper, we also discuss how to use partial attack information through information set decoding, and we show practical attack results of the implemented Reed-Solomon decoder of the reference implementation. That concludes my talk. Thank you very much.
Thank you, Thomas, for this presentation. Do you have questions on the chat? I will try to wait a little bit more because questions arrive for the previous presentation. So we will take them maybe at the end. So Thomas, maybe do you know if there is ways to implement countermeasures for your attack?
That's a very good question. So we're actively doing research on that. Right now, it seems that it's quite hard, since if we look at this block, at the block here again, so if we look, for example, at this, exploiting the hash function here, so this is dependent on the message, and then if the message changes, the whole hash function changes. But nevertheless, also the whole recomputation changes here. So also the seed gets changed if M changes, and also then the whole recomputation changes. And this, so we can use all the samples here in this recomputation for our attack, which is quite a lot of leakage. So the countermeasure would be to have a completely masked first of all the re-encryption, and also we have to make sure to find countermeasures for the decoder. We are actually doing this right now, but it seems that it's not that straightforward.
Okay, and so you are saying it's possible to implement countermeasure, but the cost will be high? Or?
Yes, that is true. And also for the decoder, there is not much, as I said, there's not much literature on how to mask decoders, and therefore it's kind of a new field. And we've been working on this for quite some time now. Maybe I'll present something in the future on how to secure this.
Okay, thanks. So are there other questions? I don't see other questions in the chat. So again, maybe if questions come, we can come back to you at the end of the session. Thank you for your presentation. And so the next speaker is Guillaume Goy.
Hello, can you hear me?
Yeah.
Perfect.
Hello.
Put my presentation. Can you see the slides?
No, it's coming, yeah. So Guillaume will present a new key recovery side channel attack on HQC with chosen ciphertext.
Yeah, so thank you for the introduction. This work is a joint work with Antoine Loiseau and Philippe Gabory. And I will present you this key recovery side channel attack on HQC. So Thomas already presents the HQC crypto system, so I will do really quickly. So during the key generation, you have two parts of the key, X and Y, which are a vector of small Hamming weight. And during this attack, we will try to recover the value of the support of Y. And during the encryption, you can see that the message is masked by adding an error that is removed by decoding this value v minus u times y. So we will focus on this decoding part, and that's the part we try to attack with sidechannel. So the decoding algorithm is up to choice of the author of HPC, and they choose to use the concatenated Reed-Solomon and Windmuller codes that are built one after the other, even in the implementation part. And we'll focus on here the decoding of the Reed-Muller. As you can see, each block are independently decoded. That will be useful for our attack. So the idea of the attack is to select the value of u and y equals to 1 and 0, which leads to decode the secret key y. Thomas already talked about the re-encryption part. So yes, obviously this ciphertext here is not a valid ciphertext, so it will not pass the re-encryption part. But given that we are looking at the side channel leakage of the decoding part, and that the re-encryption part occur after, the invalid ciphertext is not a problem for our attack. So after seeing this observation of decoding the value of the secret key, we will slightly modify the value of v, that is one of the part, that is a part of the ciphertext, to find some collision with the vector y. And the idea is to find finally a value of v that is equal to y, and we reach the decoding of 0 that we can detect with sidechannel. So our attack is based on sidechannel oracle that is able to determine the number of errors that are created by the Reed-Muller decoder. Okay. So if we assume that we have such an oracle, we can first try to decode the value of y. So we will have some value b0 to bn1 minus 1, which are the number of error in each block of the Reed-Muller of the decoding of, which are the number of error decoding by the Reed-Muller decoder within each blocks, and we select these values as the reference value. After, we can change the value of v and then redo the same operation and decoding v minus y, and we will have some other value, which are the attack value, which are different from the reference value, depending on the value of y we select. And given this attack value and the reference value, we are able to determine if we found a collision between v and y, and I will show you how. So the idea here, to be more for more understandability, I will focus on a single block of y. So we select the block of v to have an Hamming weight of 1, and we have two cases. In the first case, if there is an intersection between the support of this block of y and the support of this block of v, then the number of errors to be decoded will be 1 less than the reference value. So we can, with the answer of our decoder, with the answer of our oracle, we are able to know that the support intersect, and we are able to detect one location of the one in the vector y. And the other case, it's when the support is disjoint. In this case, we will add an error to be decoded. So the value of the oracle will be 1 more. And then we know the location of a 0 in the support of y. So yes, we can note that we have only to recover the value when the oracle outputs one value 1 less, to have all the location of the 1 and then retrieve the value of y. Okay. So yes, we did tests with the classes of small Hamming weight among the blocks, and we use the t-test leakage assessment to say if there is any leakage during our attack. So here you have the result for all the classes. So the number here represents the Hamming weight of the blocks of the read-muller to be decoded, and then we are able to distinguish between all these classes. So this leads to an attack. So for this attack, we use linear discriminant analysis, which is a machine learning tool, and that allows us to distinguish between the classes we just mentioned earlier. And by selecting a good amount of training traces and attack traces, we see that we are able to reach an accuracy of 100% with more than 50 attack traces. So this result leads to a successful attack with less than 20,000 attack traces. We are able to reach this number of traces because we can do the attack independently on each block, so which allow us to reduce the number of attack traces we use. So we present also a countermeasure that is based on the linearity of the function we target, which is the first order mass transform. So we can mask it by applying two times this function. And to show that this countermeasure is effective, our countermeasure is effective because here you can see there is no t-test peaks. So which let us know that there is no one order attacks that can work against this countermeasure implementation. And finally, as a conclusion, we present a new side channel attack against HQC, which works with less than 20,000 attack traces. We present also this countermeasure that prevents our attack from succeeding. And as future work, we can try to reduce the number of required traces by improving the physical setup. We can also try to find new target function within HQC to build new oracles, then improving this attack or find a new attack. And sorry for technical problems.
No problem. Thank you for your talk. Again, you can ask your question on the chat. Maybe one first question. How do you compare your attack with the previous one? And you have countermeasure. Can they, I don't know, apply? It's a naive question. Can they apply to the previous attack from the previous talk?
Yes, so the first difference, I think, with the previous talk is that we're able to parallelize our attack on the different block of the read-muller decoder. That allows us to reduce the number of attack traces. And yes, we also present local countermeasures, so I think it can prevent the previous attack too. But to prevent the other attack, we need to use a global countermeasure that mask the old decoding parts that is not yet public, but maybe we can publish it in the future work.
Okay. So there is a question on the chat from Tanya. Were the graph showing the countermeasure effect also using learning, or is it the pure measurement output?
So for this slide here, it's not an attack part, it's just a statistical test to show if the two sets are distinguishable or not. So here we use physical traces, but not with the attack setup, not with the linear discriminant analysis.
Okay, Tanya, I think it answers your question. Okay, and there was various questions for Marcus on the chat, but I think the questions were answered directly in the chat. So, okay, I don't think we need to come back to them. Okay, and maybe a last question for you, Guillaume. Do you think your attack is very specific to HQC, or could it be applicable to other code-based crypto systems?
Maybe you think about Michaelis or DAC, and I think this attack is really specific to HQC because we need the publicly known decoder to apply this control measure, and we also need the structure of using the secret key before decoding. For example, in Michaelis, the secret key is within the decoder, which prevents this kind of attacks.
Okay, thank you very much. So thank all the speakers of the session. And I think there is a little break, and we come back, I don't know how to say the time, at 10